potential, you have this nice Fermi sphere, that totally ignores the Bron zone boundary. If the periodic potential is sufficiently strong, then all the states in the first Bron zone get pushed down far enough that they all want to be filled, and all the states outside of the Bron zone get pushed up far enough that they all want to be empty, in which case you can have an insulator where the entire first Bron zone is filled, there's a gap, and then everything outside of the first Bron zone is completely empty. Okay? So that's with a strong periodic potential. Now the thing that's interesting is what happens when you have a weak periodic potential. Now in this case, if the periodic potential is weak, the states within the first Bron zone which are unfilled in the free electron case, they do get pushed down in energy, so some additional ones of these are going to get filled. So some of these states are going to get filled because they've been pushed down in energy. On the other hand, some things outside the first Bron zone, those are getting pushed up in energy, so some of these guys are going to empty in energy. And you'll get a picture that looks kind of like this. That there will be the states, the highest energy states in the first Bron zone, the ones that are farthest from k equals 0, do remain empty. But most of the first Bron zone is filled. And there are just a few electrons, the ones that are closest to k equals 0 in the second Bron zone, which are also filled. So it's neither the limit where the entire first Bron zone is filled, nor the limit where we just have a nice free electron circle, which ignores the Bron zone boundary completely. Now this sort of extended zone scheme way of plotting things is sometimes inconvenient, so what people like to do is they like to plot everything within the first Bron zone. We're guaranteed we can do this by Bloch's theorem. So this is the first Bron zone, or the first band, which is completely filled except for these pockets in the corners. And the second band, well, now I have to move everything from the second Bron zone into the first Bron zone by moving everything by a reciprocal lattice vector. So this little half moon gets moved over to here, this piece here gets moved over to here, and so forth. And you can just translate everything until it's back within the first Bron zone, and you can think of this as being the lowest band, and this as being the second band. So since part of the lowest band is filled, and part of the second band is filled, what we have here is overlapping bands. And even though we have exactly the right number of electrons to completely fill the lowest band, the energy is better if you mostly fill the first band, and then fill a little bit of the second band instead of finishing filling the first band. Okay? Is that clear? Good? So this is what happens in calcium. This is a little hard to see, but let me blow it up a little bit. So this calcium is FCC, so it has this funny shaped Bron zone boundary, truncated octahedron, and this yellow ball almost completely fills the Bron zone, but not quite. The yellow ball is slightly inside the Bron zone in a lot of places. The places where the yellow is not drawn is where the boundary has hit the where the Fermi surface has actually hit the Bron zone boundary, like along this region. The Fermi surface has hit the Bron zone boundary, so it's not drawn as yellow in this picture. Okay. So for much of this picture, the Fermi surface is actually all the way at the Bron zone boundary. Then in the second band, there's a little bit of this thing that's almost a Fermi sphere that's peeking into the next Bron zone, and you get these little pockets, which are the analog of these little pockets, into the second zone. Okay? So calcium, even though it has 2 electrons per atom, it could be an insulator, but the periodic potential isn't quite strong enough to completely empty the second band and put them in the first band. So if calcium was had a little bit stronger periodic potential, it would be an insulator, but it doesn't have quite strong enough periodic potential, so it's actually a metal also. Okay. Now, in the remaining 4 minutes, I'm going to explain a couple cases where the band structure of metals, insulators, and semiconductors actually fails. So failures of band theory of bands. And there's a very few of these. I mean, once we understand the band structure of solids, and we're going to do this in the next few lectures, we're going to be able to explain an awful lot of the physics of genuine, real solids that you come into contact with every day. But it does have a few failures. And the main failure stems inevitably from electron-electron interaction, which completely ignored. So everything we've been considering considers electrons as completely independent particles that don't see each other by equivalent interaction. Now, the first time when band theory can fail is occasionally, you can have half-filled bands, which are insulators. Actually, maybe I shouldn't call them half-filled bands. Put that in quotes. What's more proper to say is you can have, say, 1 electron per unit cell, and you get an insulator. These are known as Mott insulators. Mott insulators. And the physics of the Mott insulator, it's actually probably easier to understand than the band insulator. So you imagine a bunch of atoms lined up in a row. And imagine that the Coulomb interaction, Coulomb repulsion, the Coulomb electron-electron repulsion is very strong. Such that no 2 electrons on 1 atom. Okay? So you can imagine having the electron-electron repulsion be so strong that 2 electrons will never sit on the same atom. In which case, if you have 1 electron per atom in this system, well, okay, so you get 1 electron here, 1 electron here, 1 electron here, 1 electron here, and so forth. And then imagine heating this up or applying an electric field to it and asking, can the electrons move? Can the electrons carry current? Well, in order for them to carry current, this electron has to hop to the neighboring site. But it can't do that because the energy to sit on that site is very, very large, and it's forbidden to put your electron on a site where there's already an electron. So what you effectively have is basically a traffic jam. That no one can move because its neighboring sites are already filled. This is known as the Mott insulator. And there are a few materials, things like nickel oxide, cobalt oxide, which are turned into insulators because of the strong electron-electron repulsion. There's a second